Hello, friends. The most amazing thing about our universe is its size. How unimaginably big it is, but this is also the most disappointing thing. Just think, if today we use our powerful telescopes to find another planet like Earth in a galaxy that is habitable for humans, it will take centuries to reach there. In fact, it is impossible for any individual human to leave this galaxy. You all know that Earth is in the Milky Way galaxy, and the closest galaxy to the Milky Way is the Andromeda Galaxy, which is approximately 2.5 million light years away from Earth. So, if we use a spacecraft to reach there, the normal speed of a spacecraft is 28,000 kilometers per hour. At this speed, it will take 94.5 billion years to reach there. Not only this, if we somehow develop the technology to travel at the speed of light, it will still take 2.5 million years to reach there. This is really disappointing. What is the point of finding all these planets when we will never be able to travel there? But if there is a shortcut to travel outside the galaxy, a shortcut through which we can complete this journey of 1,000,000 light years in just a few months, then these things definitely become interesting. These shortcuts are. Friends, Wormholes. My favorite space film of the year 2014, Interstellar. Once again, I would like to mention here that in this film, it is shown that when Cooper and his team leave the Earth and go in search of habitable planets, in search of other planets like Earth, they travel in other galaxies. They reach from their galaxy to another galaxy. This is the scene in the film within a few minutes when Cooper's team passes through a wormhole. According to the film, this wormhole was discovered by NASA near Saturn's orbit. It is mentioned many times in the film because later it plays a very important role in the plot of the film. But the most interesting thing is that this concept of wormholes is not science fiction, but is based on real science. Before understanding what exactly are wormholes and how can we use them, we have to come back to Einstein's theory of relativity. I also talked about it in the video on black holes, and also explained the basic concept in that video. Now let's go a little deeper into it. When Albert Einstein wrote his theory of relativity, it was written in a set of equations. These equations, the set of these is called the Einstein field equations. They were first publicly revealed on November 25th, 1915, when Einstein submitted his paper to the Prussian Academy of Sciences in Berlin, Germany. In total, the field equations consist of 10 separate equations, 10 nonlinear partial differential equations, but they can also be represented in short by a single equation. And that one equation looks like this. Capital G mu plus small g mu equals 8 pig divided by c to the power 4 in TMM. Don't worry, we won't go into the mathematical details in this video because there is a lot of complexity in this one equation. If you expand this one equation, look at how the steps look. Even if you love math, you will be blown away. These equations roughly tell us how matter and energy influence the curvature of space-time. Albert Einstein said to visualize this. Imagine a big mesh. When you put objects on top of this mesh, it bends down due to the weight. The mesh of space-time also bends in the same way. The curve becomes bigger and bigger than the weight of the planets and stars. The more the gravitational force of a planetary object is, the more the mesh of space-time will curve around it. Now, the interesting thing is that Albert Einstein himself could not completely solve his field equations. He could only find an approximation. The first person to solve these field equations in a specific case was Carl Schwarzschild in 1916. He calculated exactly how much the curve of space-time bends, and how it bends in the case of a single ball of a mass. It was Carl Schwarzschild's solution that helped scientists understand what would happen to the concept of singularity if this mass becomes infinitely dense. The curvature of space-time will wrap around it so tightly that this region will be completely pinched off from the rest of the universe. It is because of this that scientists were able to theoretically prove the concept of black holes, and this happened 100 years ago. Actually, several decades later, in 1916, scientists were able to prove the concept of black holes. In 2019, it was for the first time that scientists took a photo of a black hole. So, roughly, what I am trying to say is that one solution of these field equations was black holes. Theoretically, we already knew about the existence of black holes about 100 years before they were discovered. And the thing is that there is another solution of these field equations, friends. Wormholes. You might be wondering how two solutions are coming out by solving one equation. I would say, remember in school you studied quadratic equations. This simple equation also has two solutions. X equals 2 and x equals 3. Both of them fit. So, if you look at Einstein's field equations, they are much more complicated. They actually have many solutions. Wormholes are one solution, and its scientific name is Einstein-Rosen bridge. This name comes from Albert Einstein and his assistant Nathan Rosen, who together found the solution in the year 1935. It's very easy to understand wormholes. It is basically a shortcut that connects 2 points of space-time. First, I will explain things to you in 2 dimensions so that it is easy for you to understand. It is easy. Look at this paper. There are 2 points A and B on this paper. If you have to go from point A to point B, what can be the shortest path using the direct straight line that connects A and B, right? There cannot be any shorter path than this in 2 dimensions. A flight connecting Canada to New York directly in a straight line will go over Africa, but in reality it will not be the shortest route because you are thinking in 2 dimensions. The shortest route will actually be Finland, Sweden, Iceland, Greenland, and reaching New York, which when seen in 2 dimensions seems like what a long route it took. What was the need to go over it? But if you see it in 3 dimensions, you will feel that it is quite obvious that this is the shortest route. In 1957, scientist John Wheeler published a paper on Einstein-Rosen bridges and compared it with a similar analogy. He said there is an apple and a worm is eating that apple. A worm goes from one side of the apple to the other and travels through the middle. And then eat it instances of it traveling on apple's surface, like our airplanes do, around the circumference of the Earth's surface. So, by doing this, the worm will travel a short distance. In a way, it has taken a shortcut in space-time, and Wheeler named this term wormhole, and this is where the word wormhole originated. Friends, when you search on the internet, you will find many such diagrams. Basically, the same thing that I did with the paper, 2 points connected through a hole. Here we are imagining our space-time mesh. On it there is an object which has a very high gravitational force. So much so that the curvature of this space-time has been bent so much that it has come out from the other side. This space-time mesh has folded on itself, one over the other, in the same way as the paper was folded. And this wormhole became a shortcut to travel from one galaxy to another. But in all these visualizations, the same dimension problem has been tried to be represented in 2 dimensions.